Okay guys, in last video, I explained how to determine the optimal digital regions for a digital receiver in a digital communication system. In this video, I'll show you how we are going to actually implementing this scenario in our digital communication systems. In previous video, we derive as our decision variable as SI norm squared minus R SI minus N naught ln Pi. In order to make, we want to actually, in that case, we want to minimize this variable. For the sake of easiness, I take my new, actually I take the same decision variable, but the thing is, I get the negative value of the previous decision variable because it is make calculations more easier. I get R times SI minus SI mod squared plus N naught ln Pi. So this is my new decision variable. In that case, actually the thing is, we can see that this is as I lastly mentioned, this is the projection of received signal to our constellation point or to our to our signal SI. It means we have a signal SI on our constellation diagram. This is actually a projection onto our receiver signal onto the signal. So if we take two vectors, in order to simplify this, we can take two vectors as V1, as I just take as A, B and C, and I take V2 as D, E, F. We know the Euclidean product can be written as, between those two vectors, as AD plus BE plus CF, which is equivalent to V1 transpose V2 or V2 transpose V1. It means it is transposed into the matrix multiplication of these two. Variable of D, E, F or D, E, F times A, B, C. Actually, this is R equal. Now, the thing is, if we can write this received vector in terms of our basic signals, like the components are correspond to in as a placement Psi1, Psi2 and so forth, and SI. SIs are we also written in our basic signal space with index denoting how much it contains from each of our basic signals Psi1, Psi2 and so forth. So if we can written this, we can write this as a matrix product. Or equivalently, for signals, it is actually, this is how we're going to do it with matrices when it's representing it in our signal space. But if we do in real signals, we define, if we take two signals AT and BT, we define the inner product between those two signals as integral over minus infinity to plus infinity AT times BT. This is our integral. With knowing that, we can take our decision variable as di equals R times SI minus SI squared plus N naught ln Pi. This is my new decision variable. And since in order to make things easier, I call this as ci. This is a scalar, and also this is a scalar. I call actually this is our dot product between our received signal and our ith the ith signal, our transmitted signal set. So we can write this as our vector transpose is I vector, because in this case I written this in form of our basis vectors psi1, psi2 and so forth. I write in this as a vector which is corresponding to our basic constellation points, basic signal sets. In our actually this is actually coordinate vector in our signal space diagram. So in order to do that, so why I am doing this? We can see that we can calculate this term with prior knowledge. It means this term has nothing to do with our receiving signal. We can calculate with our SIs and PIs. Also, the some information of the channel, that is the noise spectral density. So I take this as CI. So I can implement this as, if I receive some signal R, I split it into M paths, and I place an integrator here, dt. I place and also some integrators here, M integrators here. Actually, I integrate here when each integrator, actually before passing through the integrators, actually run out of the order. Sorry for that. I have n signal paths. Before going to integrator, I should put a multiplication here, and here, m path. When each of the time I multiply S1, S2, S3, which is I know already, and pass through an integrator now. And I pass through an adder. I add up each CIs to these components. And finally, I fed this to my decision making board. It receives the corresponding D1, D2, D3 into Dm. It means the decision values. Based on the decision values, it output what is the signal received. Or actually, I can take it as I'm not going to say it is SI. I just write MJ or something. Or it is not necessary. Let's say some SD. It is actually decide what signal it received. Looking at its implementation, clearly there are this is M. There are M integrators and M memory, because we have to memorize these CI terms. These are calculated. They don't recover any knowledge of our received signal, and we can store them. So we can derive what is our decoded signal by using this formation. So actually this is very much costly. Thing is, imagine we use two-dimensional case. We can have, if we take some constellation diagram like 16 QAM, which is uses two signal dimensions, but they have 16 signals to transmit. It means we need 16 integrators. If we use our signal set contains 1024 signals. We need 1024 integrators. It is pretty much costly. We have to bear a lot of integrators in order to implement this thing. So there is an alternative without implementing. Actually, we are without implementing these guys, these integrators. We do another way round of this. We got our received signal. This time, I split these terms up n terms, n branches. And each of the time, I'm going to multiply this with my basis signal sets. And psi n. And I'm going to pass through this an integrator. Now what I'm going to do is, I'm going to feed this to my some sort of control unit or computer or anything the system might decide, the decision making process. Actually, it will receive this component is equivalent to my R vector. Rn. It means I can written R with respect to my my basic signal set. Basic signal set. I can write R1, R2, R3, and Rn. Actually, this receives the R vector in my basis signal set. In this, I calculate R transpose Si dot product minus Si squared minus n naught ln pi for each signals and calculate my decision variables again, d1, d2, and dm. I calculate m variables, and based on those decision variables, I can output my signal again, which is the decoder signal. The thing is, now I am only using n integrators, but I have to memorize the Si components as vectors, and also I have to memorize Ci's component as vectors. Previously, I generate those signals. I'm not going to memorize them, but in that case, we need more memory element to memorize these Si's. And also I have to do a lot of computation in order to calculate that, because all the calculation I gave to the computer. I reduced the number of integrators, but I increased the number of memory elements and the processing. So actually these have pros and cons, but we can, if you're going to choose between those two approaches, it depends on our requirement or our applications. What if we require a compact design with less integrators, we should go with the second approach. If we need compact design but we can afford the usage of memory, we can go with the second approach. So, and the third approach is, it is pretty much different than this. We are using integrators here because implementing integrator is pretty much costly and pretty much space efficient because it is using capacitors. So we're gonna deal with this like this. If we take two signals, we know, I previously tell you AT dot BT is defined as this, minus infinity to plus infinity AT times BT dt. So I'm gonna see something like this. I get linear time invariant system whose impulse response ht, and I fed the system a signal xt, and I give an output yt. I can write yt as minus infinity to plus infinity x tau times, actually I can write x tau times or xt times, I can write write x lambda times y t minus lambda d lambda. This is my convolution. By observing that, we can closely relate that. It means if I choose my integrator, I fed this signal as before, or simply I can write this, sorry, this is not y, this is actually h. Or I can write this as, in the same way I can write, it's minus infinity to plus infinity, ht minus x t minus lambda, sorry, x lambda d lambda. Observing this, I'll do this slight modification to this to implement inner product using a linear time invariant system. I fed AT as before, but I use this as B T minus T. And I get my output, let's say GT. I can write this GT as integrate over minus infinity to plus infinity B T minus lambda times A T minus lambda dt. It is corresponding to this. If I sample this output at t equals capital T, I can get gt as integrate to minus infinity plus infinity b t minus lambda times a t minus lambda dt, which is actually the inner product of my two signals, because when integrating my minus infinity plus infinity, the range is actually doesn't matter. So this is actually I can implement this scenario using my as a linear time invariant system. Actually, we can see this. What is the important thing is I can get rid of my integrator part in my application system. This is actually called I implemented using a linear time invariant system, and I don't need to use integrator anymore. So this is actually quite excellent result when I considering about the pros of it. The amazing thing is we can use this to determine our signal as well. The thing is, if we need, actually the thing is when we actually this result is actually the thing is actually this is I have two uses mainly. The first thing is, using this idea we can replace each of these integers as a linear time invariant system in our previous approaches. The second thing is this. Let's say if we transmit a signal like this, our signal is S plus N. I am gonna receive this information signal using like it is pretty much easier to write RT equals ST plus NT, which is my signal, and I'm going to decode this signal with an impulse response HT. HT, actually I'm going to decode this as HT minus lambda. So the thing is HT minus T, sorry, T minus T. So using an impulse system system which having impulse response of this. I'm gonna decode. So having knowing that I fed this signal to this system, let's see what happens. Let's say my output would be YT or something. Right. The thing is this. My output will become YT equals minus infinity to plus infinity or T minus lambda times H. It's actually T minus simple T minus lambda d lambda, and I can write this as minus infinity to plus infinity S T minus lambda plus N T minus lambda plus H T minus lambda d lambda. This is actually, we can write this as minus infinity to plus infinity S T minus lambda plus times H T minus lambda d lambda plus minus infinity to plus infinity. My noise part comes into play, and T minus lambda plus H T minus lambda. And I'm gonna sample this at T equals T. I'm gonna sample it at T equals T. So I get this as the inner product of S T minus lambda. When I closely looking that capital T minus lambda times H T minus lambda plus my noise signal N. This happens again. My noise signal T minus lambda times H T minus lambda. This is actually basically I will do two inner products by using the fact that the inner product equation I write here. I'm using this fact. So the thing is, I don't need this part. This is actually unwanted part. But I want, when I decoding, I want to, in my decoding signal, or I decoding variable in the sense, I want a maximum of my receiving signal. I want to include a maximum of my receiving signal in that. Let's say, let's look back to some our geometrical knowledge. If we given two vectors as V1 and V2, we know V1 inner product V2 when I be using an Euclidean inner product, it is equal to norm of V1 times norm of V2 plus cos theta. It means we get the maximum results when theta equals 0. It means actually V1 will equivalent to lambda times V2. Actually, I don't lambda, I will use some other letter as alpha or something. It means two vectors are parallel. The same theory applied to this inner product as well. It means I can take the maximum value of this inner product T minus lambda plus H T minus lambda when it is actually maximum maximum result when I can maximize this when S T minus lambda, or I take some constants beta equals H T minus lambda. Or in another sense, my impulse response H T minus T is equal, it is nothing to do with the variable. beta times is t minus lambda. Actually, when beta is positive, I get a positive answer. If beta is negative, I get a negative answer. But when it's considered norm, it is no matter which way we are going to use. The thing is this. If we always use to beta be positive, the thing is this is called matched filtering. It means if we want to decode a signal using an impulse response, using a linear time invariant system, our impulse response of that system should be matched to our data signal. This is called match filtering. In that case, we can maximize the energy of our signal in our decoded signal. Actually, it is quite interesting. Without knowing that fact, actually, in my previous two approaches, I did the same thing. Actually, the integrating part we can see as a linear. We can see that we can replace it as a linear invariant filter, but that the impulse response of that actually our signal match to our signal, which is should be equal to equivalent to this. If I replace those with in that case, if I replace with those with linear time invariant system, this should be equal to Si times t minus t, and I should sample like t. So that is the main purpose of this. The other thing is this. It is very nice. The including this t here. This is actually not lambda. This is t. The thing is this. We can replace. If we plot this thing. If this is my st. This is my st. I can plot my st minus t as this. Here's my t here. And the thing is actually most of our signals are impulses, so we can write this as my st, and I can write this as, I cannot match the shape exactly, but I think you can imagine. We can make this t large enough to contain most of signal energy of this causal part. So we can implement with a causal filter and get rid of the integrator with this match filtering statement. Actually, previously, without knowing what is the best linear field impulse, which is the best impulse response to use to integrate this, actually we choose the optimal one without considering the fact that the optimal match filtering principle. Actually, we just replace integration with linear invariant filter with our known signals, and in fact, again, after that we show that it is the optimal choice if we use an impulse response to decode our signal. The optimal choice to the impulse response, it is the impulse response matched to our data signal. So actually, the thing is, in first part, I show two approaches and I show how to get rid of the integers, and afterwards, with match filtering principle, we justify our choice, and it is the best choice, and it is actually a quite good choice to use. Actually, this is the thing basically covered in our module, and I think hope it is clear for you guys. And the other part is probability of error and so on. I think I discussed it earlier because I'm not going in order, and I explain it. When I explaining, I move things a little bit and make more simpler to you, just a basic idea. So this is actually the end of the whole theory covered in that module, the basic ideas, not the whole thing. So in the next videos, which I'm gonna do is I'm gonna discuss some exam level problems and show how to use these ideas to solve exam level problems and how to use them in practice. So that is the most key important things. So you need to understand this basic thing properly, not to memorize those complex equations. You need to get the idea properly, and you can solve the problems easily. Actually, it is not much to learn there, just to apply the principles, that to see things clearly what is actually happening out there. So this is for today. Actually this is for this video, and I'm really looking forward to your valuable suggestions to improve this video.